Hey guys, welcome back. So we're going to continue on with solving exponential problems here. So we were in, we just finished off a interest one. Now we're going to start off with a half-life equation again, or some kind of growth and decay. So we're going to be using this formula here, which is very similar to the interest ones, but instead of using A and P, you're just using Y and A being your initial amount, much like the P in the previous one. Your B being your base, right? Remember, if that's greater than 1, you have a growth. So if my B here is greater than 1, I have a growth here. And if I'm somewhere between 1 and 0, I have a decay, right? Oh, I got a not responding. Okay, so good. So what we're going to do here, we're going to determine what our exponential is. I seem to have lost a little picture here, but the equation for our exponential function was a b to the t over p. Remember, our p here is our period. Like half-lives, that's usually the half-life time, but sometimes they just give it to you. Also, like in the interest one, is very similar to that. We can think about the compounding period. How long does it take for whatever this b value is to take place? All right? How many times do you perform an interest calculation? How many long times do you get to a half-life? So this little number here, this 5,730, that is your P. It's how long it takes to get 1/2 of what it was before. So my P is going to be in years here. So that means I'm going to assume my T to be in years as well. I just want to make sure that they are the same. So my T here is going to be in years because this was also in years, right? Now, we learned this in physics and stuff, but this is what we call carbon dating, and we use this similar half-life for this as well. So we want to know what the equation looks like to start off. We can use some information up here to create more meaningful variables rather than using y and x, but since that's what this equation up here was, that's what's given to you on the formula sheet as well. Let's use this formula as is. We don't know anything about the A, but A is usually either represented as percentage or grams or radioactivity in these kind of questions here. It's what you start off as. Sometimes it'll be 100%. So I'm just going to, because down here I can see down here that I have a particular 100 grams. So I know for this part of the question down here, my A is 100 grams. Right? So I know that much for that question. Up here though, I don't know that, so I'm just going to put an A here for now because it could change as it go. Our B here, because they are talking about half-life, that's a half, and I have T over 5,730, so that's my P there. I'm looking for the T for some of these. Here, we want to know how much sample will be after 15,000 years. So that's, I would almost say approximately 3 half-lives later. So like if 3 half-lives, this would be cubed, so it would be like 1/8 of my sample. That's my approximation, like 1/8 of 100. Well, let's just see if that actually works out. So I want to determine that. So here we got to start off with 100 grams. That's going to be my initial amount. Got that B value of a half, and here we're going to put 15,000 into this equation here, right? There's really not much you have to do here. You don't have to rearrange anything. We're just going to plug it in as is into my calculator. Right? So I'm going to do the exponent part first, and then I'm going to times it by 100. So I'm going to raise this to the power of 15,000 divided by 5,370, and then I'm going to times it by 100. Right? So once we do that, we end up getting about 16, and I want to the nearest hundredth. So that's 2 decimal places. Nearest tenth is 1. Hitting the right-click button on my pen here. So 16.29 grams, which is approximately an eighth of this number. No. Well, just a little bit more than an eighth, but that's fine. All right, it's not quite 3 half-lives here. Looks pretty good. Now it says what percent. Now this next question says what percentage. So we're looking for A, or no, we know what an A is. Our A is going to be either 100% or 1.0, depending on how you want to treat a percentage at this point. You notice that we have units for these. So whatever unit I use here is whatever I get out. So if I use 100%, my units will be in percentages. If I use 1.0, I won't have units. It'll be more of a ratio. So let's see what we have here. It says what percentage will remain after this. So I'm going to put 100% here. Put a half, 12,000 over 5730. And we do the same thing. So I'm going to go 100 times 0.5 to the power of 12,000 divided by 5730. Okay, so about 23 point, it doesn't match decimal wise, so let's go 2 decimal places. 23.42%. Yeah. So far, so good. This is pretty easy. Let's see what we have down here. How long does it take? So this is now looking for the t, question mark. So we haven't learned how to solve for our exponents. So when I set up this equation, you'll see that 1/20th of its original mass, or 1/200th, sorry, of its original mass. So if I say my a was 1 to start off with, hey, how's it going?
Oh,
All right, sorry about that. I got distracted there. So let's go back at it. Like I was saying, that sometimes I get distracted. Other people come into class, so I have to stop the video. So what were we doing here? We were trying to figure out how long the sample takes, so we're going to create an equation. So we have an A. Let's assume our A is 1. It could be 1 gram or something. Then our Y, our amount that we're trying to find, is 1/200th of that original mass. So this is going to be 1/200th of a gram because it's just 1 to start off with. So I can set my equation. So I can say this is equal to 1 over 200. I got 1 here to start off with. This is all still the same half-life equation, but this time we're going to solve for that exponent. Right? We can solve by graphing it. We haven't solved a way to do algebraically here. There's a 1 here. If this is any other number, you'd have to kind of divide that over to the other side. Oh, that's for solving for algebraic. For graphing, it doesn't really matter. You could just leave it the way it is. If you want to, you could times the 200 up to the other side and make this a 200. Because if this start off with 200, I'd have 1 gram left. But that's up to you which 2 numbers you picked here. It's either the same or either way. So let's go to our graphing calculator here. And let's see what we can do. Let's make my face again. Okay. So we're going to clear this out. And we're just going to put in the same idea. So we're going to go 1 over 200 on one side. And then on the other side, we're going to type in exactly what it is. If there was a different a value other than 1, I'd write it. But I don't see any point in writing it. Oh, sorry. Let's delete that back. I'm going to use this 0.5 rather than 1 over 2. And I'm going to raise that to the power of x over 5730. So everything looks good there. I'm going to just put my zoom back to the way it was. Yep, there's a line. Yeah, it looks pretty good. Because of the x value being 5,700, what I'm going to do here, or my period, I'm going to make my x max a much larger number. Right? You can see over here, 23% is left over after 12,000 years. So let's say our number is 20,000 years to start off with from x max. So I graph that out. You can see it kind of went down a little bit, but because my window, my y values here, will never be more than what I start off with because it's a decreasing function, I could say my y max is 1. So I start with 1. There's no point of going below 0 because remember, these have a horizontal asymptote at 0. There's a nice little graph. Looks pretty good. Now, there's 1/200th. Where is that? Well, 1/200th is a really small number, and it's really close to 0. So you can see this line here is doubly thick. It's doubly thick for 2 reasons. Because the scale is all messed up here. I can probably try to spread out the ticks a little bit by changing the scale. Rather than every 1, I can say it's every 1,000 years or so. Right? If I graph that again, I get less scales. But the 1/200th number, this number at the top here, is so close to 0 that you can't really see it. So if you want to see it a little bit better, your y max doesn't have to be so large. Your y max could be 1/200th. That's really all you want to see. You just want to see that line. So there's that line at the top here. Okay. So what I'm going to have to keep on doing is I'm going to just zoom out a little bit. So you're just going to fiddle with the numbers a little bit here. Let's say this was 50,000 instead. All right. Oh, and there's that little piece of the graph here coming down from the top because we zoomed in quite a bit to the top here. This is where it's crossing over. So I can see the crossover point. So I'm just going to go intersect, enter, enter, enter. You can see my intersection point, 43,799. So I found a time value of 43,799 years. Now, you'll get more comfortable using the calculator, changing the window around, trying to match what the question is saying, like what's my maximum y value possible. Again, if I were to go back here and change that back to 1, because that's my initial amount, this is what the graph will look like. You just can't see somewhere around here, it's going to cross over this 1/200th. So you could just kind of zoom into that area down there, and that's where you're going to see this 43,799. And I knew my x values had to be pretty large because my period, this number here, is a pretty large number. So I have to use large x max numbers here. Okay, so let's leave this open so I can use this later on. I'll just write on the side over here. So we're going to do the same thing. Population is presently decreasing, right? So that means my graph is going to have a decay function. So that means my b value has got to be less than 1. So my b value, because it's decreasing by a rate of 3% of the year, that means that I start off at 100% and I lose 3%. So that means I have 97% or 0.97 left over each year. Okay. Let me just zoom over here. The present population is this. Determine function. Okay, so we know what our initial amount is here. This is not really present, it's 2012. That's okay. So my A value is 10,777. So that's how many people we started off with here. So I'm going to create a little function here, or function. Now I'm going to start off with 10,777. I have a B value of 97, and I'm going to have T over P. And you notice that this is every year, so my P value is technically 1. So I don't really necessarily have to write this. So I got this equation, looks pretty good. Now what's the population in 12 years? So we're going to write this out, and we're just going to put a 12 in our exponent here. And I'm going to go over here to my calculator. 12. Oop. Let's clear that out and start over. Bracket 0.97, and let's raise that to the power of 12. So in 12 years, there's going to be 7,477 people left. Probably round that. Yeah, probably round it down at this point. We can't really have half a person, right? We take the population. It's your choice, round it up or down at this point. I believe rounding down would probably be a better solution for this one. Okay. What would the population be, or what year will the population reach 2,000? So I'm just going to set up. I'm going to make this equal to 2,000. Obviously, got to be more than 12. So let's write this down. And now we're just solving for t. So I'm going to go back here. We're going to do the same thing that we did before. We're going to create two equations here. So I'm going to put 2,000 on one side. So that at least tells me what my y max has to be. It has to be around 2,000, so I can see that line. Maybe I want to be a little higher than 2,000 because this is my initial amount here. So maybe 10,000 or more, so I can see more of the graph. Okay, let me just finish putting this in. So let's go to my window then. So I know what my y max has to be. It's got to be at least that 10,707. So let's put 11,000 into our equation here. You can change the scale to make it look nicer. Let's say every 1,000, so there's only like 11 ticks or so. Y min 0 makes sense. My scale, so this year probably not going to take 50,000 years for this to happen. A good estimate, maybe 20 years. let's say my scale is 5, every 5 years in my box there. And x min, we didn't change this from before because our x max was really large, but there's no sense in putting a negative number here because time can't be negative. So I'm going to put that as a 0. And then if I graph on there, looks pretty good. And you notice that there's my decay function is my line, but they don't intersect yet. So I was wrong in estimating 20. So let's see what 50 looks like. Nope, not even 50 years. All right, and then we're going to just keep on going. Let's change that to 60 because it was getting pretty close there. Yeah, it looks like they crossed right here. So what I'm going to do is I'm going to trace, intersect. Now your intersection really only works if you can see the intersection. Your calculator is not going to try to find something that it can't see. But here we solve for x. Remember we switched all our x's or t's for x's. So t is technically x here. So what year will happen? It'll be we'll reach this number. So 55 years, because it's just a little bit more than 55 years. 55 years will be slightly more than this number, and 56 will be slightly less than that number. So somewhere in the 55th year, right, 55th year, we'll get that. Now, what year is that? Well, it's 55 years plus the 22 or 2012 here. So that's around the year 2067. That's probably when that's going to end up being about 2,000 people using a model, right? Not necessarily always going to work all the time, but that's essentially how this one works. Okay. So we're done this part of the video. So what we're going to see, you can see on the bottom of this page here, it says understanding logarithms. So we are going to start logarithms soon in the next lesson. Right now, just take it a little bit easy, and I'll see you in the next video.